Hello, everyone. Welcome to our beginner-friendly Transformer architecture series, the crux of LLMs. Before we get started, I want to give you a brief overview of the event series itself. So the goal of these talks is to help you understand the Transformer architecture more in depth and generally understand what it is. And this event series consists of multiple events. And today's session is called How Transformer Architecture Revolutionized AI. This session introduces the foundational transformer architecture and explains how it influenced GenAI. So today we're going to cover, I think, two parts, right? So pre-transformer history and a general top-down architecture, transformer architecture overview. And our next event is going to be next week. So please follow our social media and community platforms to be notified once we post new events here at algoframe.io. And I just want to mention that we want today's session to be as interactive as possible. So feel free to drop any questions you have in the chat. And now I want to introduce you to our special guest today, Navina, who is a senior AI and ML engineer at Bitstrap. So thank you so much for joining us. Take it away.
Thank you for having me here.
Yeah.
Okay, so is my screen visible? Yes.
Well, yeah, just shared it. Awesome.
Okay. All right. Yeah, so let's get started. So we are going to be talking about the pre-transformer architecture and their issues, and then also the actual transformer architecture. But before that, we are going to be talking about some terms that are now cliche, but really level setting there so that we're all on the same page. And I understand that this session will be having folks from business community, non-tech, software developers. And so after a while, we want everyone to be thinking like ML developers and engineers, and hopefully the ML engineers and data scientists enjoy the perspective and the visualizations and the deep dive here. Okay, so transformer architecture is at the crux of these LLMs. Now, currently, they're being used for different modalities, for different use cases. But BOT, which was released by Google, as we see in 2018, it was based on transformers. The first GPT, the name itself is Generative Pre-training Transformers. It was also released in 2018 and was based on transformers. So clearly, this is a very important architecture. And so now, terminology alert. Um, Language models, I think we're all aware of them. We are using them day in, day out. Yeah, it's like a black box. You feed in some input, it gives you some output. Kind of like any real world black box out there, TVs or like automobiles. But really, what's happening inside is what we're going to be talking about today, keeping aside all the frenzy. And what are discriminative versus generative models? So, discriminative models are those which are used for classification. So, they're good at drawing some decision boundary to distinguish one class from the other. Whereas generative models actually learn from the input data distribution. So, they're like during training, you feed in how the distribution of data looks like, and based on that, they come up with the next most probable token or output. And so that's referred to as generative. And sequence to sequence modeling. That refers to feeding in an input sequence and then getting an output sequence. They might be of variable lengths. And this could be used for stock market prediction. You could feed in a sequence of stock prices, known stock prices, learn from them, or input text, and so on. And then these terms here. These we're going to be deep diving now. So, really talking about the building blocks of these huge things, neural nets, deep learning. and starting from the very fundamental unit, which is a neuron, a single unit. Okay, so suppose I wanted to predict the price of a house. And then for that single house, I could feed in a bunch of features, maybe the amount of exposure to sunlight, the number of rooms, and so on. So these become my features for that single input. And so these are my features. Now we've heard this term parameters so much in context of LLMs. Today, this model is released. It has millions of parameters, billions of parameters, and now even trillions of parameters. So, what does parameters mean? And so, weights and parameters are used interchangeably, but parameters is like a superset. It consists of weights and biases, and we're going to be covering all of these now. So, this feature, the first feature, how much importance should I give to it? Like in how much weight should I give to it? So the word literally means that. How much weightage should I give to this feature? And how much weightage should I give is what we will learn during training. And so machine learning is all about learning these weights. And so weights and parameters. Now, what is bias? Interesting term. So whenever I am learning something new, for once, let's keep aside machine learning. Let's think about bias a little differently. Whenever I'm learning something new, the way I react to a new situation would be influenced by what I have learned so far. And that will define my baseline response. And so that is about bias. And that is also considered during machine learning. So then this could be called as x0. And now one way of looking at it is even when my inputs are say 0, I might still want to be generating a response. And that is where the bias term helps. Now the bias term itself, like my baseline so far, that itself, if I'm open, I could reshape it. So this itself actually can be learned. And so we will represent that by another weight. And so to summarize, this is my y1 for my input x1, and this is my final output z1. And so y1 is linear in these terms, and it can be represented as y1 x1 times w1 plus, so like the weighted sum of all these terms that we see here. Okay, so this is my first equation for today. And this is how it looks like. Now, what does linear mean? What does this term linear mean now? So it means as my x increases, my y increases, or as my x decreases, y decreases, or they could also share an inverse relationship. So as my x increases, my y might decrease, and vice versa. But this is a linear relation. And the problem with having only linearity is that we could plug in and stack multiple of these neurons, but if things are just linear, Imagine this Z1, and then there is another Z2, they feed into another neuron here, and so everything remains linear. And we cannot approximate some really complex relationships. So, what is machine learning? You have some hidden true function that you don't know, that's what you want to learn, and that's what you want to mimic and approximate. And for that, neural networks are known to be universal approximators. Like, given enough memory, enough data, enough compute, they can actually approximate any true unknown function. And so, for that, they do need non-linearities. And so, what is that? And that will lead us to our third term here in terms of terminology, which is activation function. And covering all of these will mean like the next few slides will be less overwhelming because we're going to be seeing a lot of this. So let's talk
Yeah.
about this.
Just before we jump into this, I guess a quick summary of this, right? So I love the diagramming, by the way. Thank you so much for drawing all of this. So neuron is like that circle that you represented, kind of like the basic unit that you mentioned, right? So the weights are those like W1, W2, W0, right? That you mentioned. So this is essentially means how much importance we give to every single parameter, right? So parameters are the actual, I guess, dimensions, right? Or like inputs that we accept. And would you be able to summarize bias again? In this case, so what is bias? How is bias represented in this case, and what does it mean?
Yeah, so bias is like a fixed input that
Mhm.
you could feed in each time. And the purpose of it is when your actual dimensions or fields might be missing or zero, you still might want to give and generate an output. And that's where the bias comes into picture. And then we're saying that bias itself is learnable. So
Mhm.
you could add a weight to it and adjust it during training.
Okay, okay, makes
Okay.
sense. Awesome.
Okay, so now just covering that last term, activation function. So it's like sometimes we know these neural nets are influenced by our brain structure, and sometimes we will be like, oh, this triggered something in my head. And so we're talking about an input signal and we responding to that stimuli and something getting triggered. And so that is your activation function. And that, as we see here, so let's talk about this first very popular one, rectified linear unit. And so here, as we see, as your y, so this axis represents your y, as it increases, z also increases. But for this part, when your input is non-negative, your output is switched off, it's zero. And similarly, this is the other one. This is referred to as sigmoidal, and both this and the next one are S-shaped curves. And the difference is that this one, it squashes your output between 0 and 1. So for positive inputs, it'll be between zero point 0.5 to 1, and then in this region, it'll be squashed between zero point 0.5 to 0. And then the third one here is tan H, tan hyperbolic. And this will give you outputs between -1 to 1. And as you see, it is not linear with that input, and so it adds non-linearities, and it plays a very crucial role in machine learning. So this is how it finally all looks like. And now with this context, we will go back to what we were covering on those slides. Right. So z is a function of y, which is, this is non-linear, this is linear. Okay, so we've covered all our basic terms and we're ready to like deep dive into our next section, which is the pre-transformer era. And here we had these two main architectures, and these are still used, by the way. They're still very popular, But let's see why they were not really so good in like scaling and in terms of language models. So the first one here is RNNs, and we're going to be quickly talking about this one as well. So suppose we want to be predicting the stock prices, and we already have yesterday's and today's prices, and we want to predict tomorrow's price. Quite a bullish market. And here our input is this yesterday's price, and we will, as we just learned, add some weight to it, and then we get predicted value for today. But we already have today's value here, right? So this what we learned, and this we will just call as some activation function. So this what we learned, we will actually feed it back in, and we will add some weight to this. Okay, and so now in the next turn, or in my current state, instead of yesterday, we will be feeding today's value here. So today's value plus the learned value of today that we already had, and based on that we get this predicted value for tomorrow. Now this is a little difficult to visualize, right? So let's simplify this. So another way to represent this is what we refer to as unrolling the network. So that is another new term that we are now introducing. Okay, so now we will simplify this a bit. Okay, yeah, good enough for now. And here we show today's value and the predicted value for tomorrow, which is what we want. And this that we were feeding back in, this feedback loop instead can be shown here. So we sum it up here, and now this makes sense. Yesterday gives an output for today, but we already have the output for today. We already know the value. So instead we feed it to our next iteration, and that's how we get the predicted value for tomorrow. And now suppose we had a leakage. So we already knew the price for tomorrow, and we instead wanted to predict the price for day after. And we can do that. So we create another such loop here, and we feed in tomorrow's value and then predict the value for day after. And so this operation here is referred to as unrolling the network. And with this, what we have here is our vanilla RNN, vanilla recurrent neural network.
Mm-hmm.
And with this context now, let's go back to the slides so that we are able to tie these things together better. So now when we look at all of this,
There's also a quick question afterwards. I'll let you finish and then yeah, go. Yeah. You want me to go? Okay. Sorry. If you can you go back to your diagram, like at this draw.io?
Sure.
Yeah. So essentially, like again, to kind of reiterate, every, maybe I'm not saying it right, but every neuron, right, it has this activation function, right, as you explained on the previous page, right? There are different activation functions that are used to calculate the output, basically, right? And here, what happens is that, as you said, there is this term unrolling the network, right? Is which essentially means just looping until we get the correct result. Is that accurate somewhat, or? Okay,
Yes,
perfect.
you summed
Okay,
it.
awesome, sounds good. Just wanted to clarify. Yeah.
Okay, amazing. So now with that context, let's move forward. So now what we see, we've already covered. You have some input, you have some weight attached, bias, and you could add some more weights here, but then you essentially get an output. And if the output is already known, it's fed back in. So these we are already aware of. And it's because of this loop that this network is called as recurrent neural network. And so this is the unrolling operation. And then this is very important. So let's talk about this a bit now. Um, okay, there we just had 2 to 3 known values and we had to predict the output. But in case of, for example, stock market prediction, you could have 365 days worth of data already present with you. And so now your input from, say, Jan 1, 2021, you're feeding into December 31st, 2021. And so your input, as you see, as it moves through this network, it's getting multiplied by some weight. And in this case, you have like 4 5 blocks. So multiplied by 2, and then again, and then again, it's 4 times. And so we can say input multiplied by exponential, like we're seeing exponential values here now because this will become 2 raised to 4. 2 into 2 into 2 into 2, that's 2 raised to 4. And so, to generalize this even further, we can say 2 raised to number of times we unrolled this network, right? Like 4 times we're unrolling, and so that 2 raised to number of times we unrolled the network. And now, this is an issue because your input, when you feed it to the immediate next value, this is your short term path or like your short term memory. But that same path now you're using to like continue and to feed it to like your most latest cell. And so this same path is also being used for your long term memory. And so by the time we reach here, we saw explosion. And gradients. Gradients is also a very common term in ML, so let's talk about it. Gradients can be thought of as slopes. If I have to really pause and take a step back and like summarize ML in 3 crisp steps, the way I would do it is you have some input, you generate some output. Step 2, you find the difference between the output and the predicted output and the known actual output, and that gives you an error. And now you want to adjust that error. That's your step 3. And to adjust that error, you want to adjust the weights that you just learned. So you want to adjust them. And that rate of change of your error with your parameter, adjustment in your parameter, is actually referred to as gradients. And so, like imagine me as a human, I'm learning something new. I would want to learn at a stable pace. If I learn very quickly, it's too volatile. If I learn very, very slowly, then like, I will not be able to catch up. So, in that sense, we just covered exploding gradients. And so, why, if this rate of change, if the slope is too steep, gradients are also referred to as slopes. And so if the slope is too steep, then you will not have stable learning and you will have too much fluctuations. You will not reach that minima where your error is minimized, and we wouldn't want that. So exploding gradients, not a good thing. Now to complete this, what is vanishing gradients? So these weights, imagine if this were point 1 and then point 1 and point 1. And so now by the time you reach here, you have like a very, very, very small value. And so the impact of your input is diminished. And so that's referred to as vanishing gradients. So how do we solve for this? And with this, we are at the end of RNNs. And so any questions at this point before we move on to our next architecture for LSTMs?
Yeah, I think like first of all, thank you so much for simplifying it as much as possible. I think yeah, it looks very interesting. So I guess to summarize and kind of combining all the questions together, right? As like essentially the issue with this architecture, right, is that it kind of like again overall it loops, right? So it, as you said, if we start from today, it predicts tomorrow, then after tomorrow it's like another prediction, and so on and so forth, right? I think, and then one of the problems is that exploding gradient. So what gradient essentially is like those training cycles, right? If the weights change too much, right? Essentially, it means like those exploding gradients happen, right? Is that kind of like a correct summary, you would say?
Yeah, so like weights will change. We could have a lot of training cycles, but we want to be changing these weights
Hmm.
gradually, not very abruptly. So neither do we want to take very massive steps towards minimizing our error, because if we just think as humans, if I want to learn something and I like really learn at say 2x speed, actually it'll be very volatile.
Hmm.
And so I want to do it very
Yeah.
gradually. And then the other thing is, if I move too slow, then it is important to pass this input into the next one and so
Hmm.
on. But you don't want, by the time you reach the end where your output is known, like, and your output is generated and you have your known actual value to compare with, by the time it reaches your, you don't want your input to either explode just because of these paths, and you don't even want it to be too diminished.
Hmm. I see, makes sense. Okay. Cool. I think we can move on for now. In case there are some questions, I'm sure there will be. I'll let you know. Cool. Awesome.
Okay, amazing. So, oh, now this looks so overwhelming. So many colors, so many blocks. What is happening here?
Bright,
but we
bright and beautiful.
so
Yeah.
but we will simplify this, and really it is based a lot on what we already discussed. So now in this next architecture, they tried to have two different paths for the short term and long term memory. So the short term memory is represented by the pink line here, and this green line here represents the long term memory. This is known as the cell state, this is known as the hidden state. And this is our input, our first input, and the short and long term memories to begin with, initially they will be zero, and then the fun begins. So, for once, let's leave this slide aside and let's again talk about how we function. So, I read something new and I will move that from my short term memory, it will move to my long term memory, right? I will retain it. And then when I want to use certain parts of my long term memory, I will fetch and recall certain bits, because my long term memory is like an entire dump. So I will pull out the relevant parts and use that as context for the immediate problem that I'm trying to address. And so you have your short term and long term memory. So parts from your short term will move to your long term memory, and your long term memory, again, it will be used to generate your short term memory. Now, with that context, let's look at what we have here. So, first, this part here. Again, now we understand what we see here, these various weights. You're summing them up, you have a bias here, and then you have this activation function, and this one is sigmoidal, the S-shaped function that we saw here. So this is sigmoidal, and it gives you an output between 0 and 1. Now 0.96 in percentages, it can be said as 96%. So it will fractionize your existing long-term memory. And so this is some output, 96% of your long-term memory, and that moves forward. But as you see, you no longer have those weights on this path, so we will not see that explosion happening as much. And then the short term memory, again, you have certain weights and biases and activation function. In this case, again, it's the sigmoidal, and it will generate a percentage or like a fraction of this term here. So what is happening here? So again, here using the tanh function, we generate some output, and that is going to be your potential long-term memory. And so percentage of your potential long term memory is what is going to get passed forward and move into your actual long term memory. So, your existing long term memory and your potential long term memory combined together will now give you a new long term memory. And so now that is how your short term memory got moved into your long term memory. And this last bit here, as we were saying, we will use our long term memory to recall and to use a portion of it as our short term immediate context. And that is what we're doing here. So here you have your potential short term memory with this tan, and then you add or consider a percentage of it, like you fractionize it by this number between 0 to 1. And so whatever this number is, a percentage of it becomes your new long term memory. And this gate here, it's actually, although it's used to like remember a percentage, it's referred to as your forget gate. And then this block here, it is referred to as your input gate because it's moving things into long term. And this your is referred to as output gate because this generates your short term which gets propagated
Mhm.
forward.
The That I love this explanation. So essentially, like the main difference between the previous architecture and this one is that it has this long-term memory, so it helps us avoid those exploding or vanishing gradients, essentially, right? So that's in a nutshell, essentially.
Yeah, because here we were adding a weight to the long term path and that was causing an issue. Whereas here, while we are considering a fraction,
Mm.
but we are not really multiplying it directly by large or very small
I
values.
see.
And so we are better sorted
It's way
now.
more accurate this way. Yeah, because we have like again this long-term context, right? And then short-term context, and we are like this long-term context or memory, I guess, it affects, right? How or I guess I think I understand it generally. It's just a little bit
Yeah,
hard to rephrase, but essentially,
yeah.
short-term memory isn't what defines this long-term memory, right? And you do those, as you said, like fractional calculations to see how um,
How we can stabilize our learning
exactly. Yeah, yeah,
and
yeah.
have these explosive or vanishing gradients which will lead to like a lot of fluctuations and oscillations, and so you won't have very stable learning. And yeah, so that way you're able to like still pass
Mhm.
forward context in terms of sequences.
Makes sense. Makes sense. Awesome.
Okay, and so now that we know how this block looks like, one unit looks like, let's stack them up together. So this is how now each word will be passed through an LSTM unit, and we could use multiple units for each word like we see grayed out here at the back. And the advantage of that is that it helps in learning different nuances because you could have different weights in each unit, and so you're learning a different representation, some extracting some different thing from your input. And this helps in learning complex patterns. So we also see your encoder and decoder, which are going to be part of our transformers. Um, Now, it's very important that we remember our initial words because imagine if this is lost and it's not correctly retained by the time it reaches the output. So then, eat, instead of don't eat the delicious looking and smelling pizza, we have eat it, and that's an issue. So then how do we solve it? So what we're saying is, although LSTM units improvised on the previous architecture, there were still issues because they also couldn't retain very long-term windows. And encoder and decoder, what are these blocks? So an encoder will take in some input and it will generate a learned vector representation, some representation of your inputs that are fed in. And your decoder, so again, like it's just like this word state. Encoder encodes something, and decoder tries to decode it. So it will try to decode what it got from the encoder and try to predict your most likely next word. And so this is how encoder and decoders are used together, and this could be supported using LSTM units. Now, before we talk about, so far we saw the issues with our LSTM as well. Now we will do some detour. So, okay. Yeah, before we talk about our actual transformer architecture, let's understand why architectural patterns are so important. And so we have software architectural patterns like broker architecture, client server architecture, layered n-tier architecture, and all of these event driven architectures is something that we in our software development community and even in our AI engineering, etc., we do use all of this a lot. And then we have design patterns that are one level lower, I would say, because they deal with like object oriented programming and real entities, and like, so how do you link them and all of that cool polymorphism and stuff. So how do you inherit well, and they also have their categories, subcategories, and different patterns therein, and they address specific problems. And so, an architecture gives you a structured approach to building complex software systems. It gives you a roadmap. It helps in building robustly and scalably. And I just read it out from your directly, like as is.
Yeah. Uh,
And um, did you have something?
yeah, there is one question, but I'll let you finish this slide first, and then yeah, we can jump into it. Yeah.
Sure. So, we usually have some problems, and to address those problems in a repetitive, reusable manner is where we come up with patterns and architectures. And so, let's, before even looking at that architecture and like talking about its blocks very dryly, let's talk about what problems were we trying to address here. So if we talk about Gen AI, you have an input, it generates an output, and then that output is fed in again to generate the next output. And this is very clearly visible, especially if you use your AI or your LLM in streaming mode. Very clearly visible, one word and then the next, and so on. And this is an output from GPT-2, like a very earlier output. And so we have some phrase being entered and then some output. And really, it's so related to your input. And this is important because with each word that is generated, you would want that it understand every other word in the input and then also understand the preceding outputs. So this is very important. And I'll pause here. Alex, what did you have for me?
Yeah. First of all, I love this analogy with the architectural design patterns to architectural patterns generally. Yeah, I think it's definitely very important to know those. Um, Question was regarding this encoder decoder slide. So if you like, I guess to summarize it in one sentence, how would you? So if you could go back to your previous slide, what is the so what is the purpose of encoder decoder again? Yeah.
Yes. So, like, you want to learn
Hmm.
an input, and for an input, you want to learn what is your best output.
Hmm.
And so, your input, you combine it because it's sequences, and you generate one learned vector
Hmm.
representation that kind of like extracts the features from your inputs and then generates one representation. So, you can say that your input has been
Hmm.
encoded, and then that gets passed to the next important block, which is decoder, and that will try to generate some output given this learned representation.
So essentially, It's like instead of treating every word as a separate entity, it says like treat this sentence as one single entity and then process it as one single input, right? And then give me one output for that, right? Okay, makes sense.
Yes.
And then one other question there was is regarding, so again, kind of summarizing the issue there. It's essentially that the emphasis can be put on the wrong words, as you said, or so essentially instead of don't eat, it could interpret it as eat because it wouldn't put enough emphasis on don't. Is that kind of the issue there, or um, yeah,
Yeah, kind of. So, like, if these words are fed in sequentially, one after the
yep,
other, so by the time you reach the last word, and if this is a very long
mhm.
chain, then your initial words will kind of be
I see.
lost. And with that, you may not capture the right
Mhm.
context, and then there will be
Yeah,
misinterpretations.
makes sense. Makes sense. Awesome. Excited for the next part for the actual transformer. Yeah.
Yes, and so finally, now we're going to be talking about the transformers. And so really, I don't want to be presenting an architecture directly and like talking very dryly about each component out there. So let's talk about what problems are we trying to solve based on everything that we saw so far. So the first thing is your words. You would want to words or subwords are referred to as tokens. So tokens, you would want to represent them as numbers because your machines understand only numbers. And then, secondly, you would want to track the order of the tokens because now we are seeing issues with the sequential pattern, and so we're planning to get away with it. And so we want to track the order of the tokens. And like we saw, we would want to understand the contextual relationship between the tokens in the provided input. So, like, how do the different words in the input relate to one another? And then for each generated output token, how does it tie to what it saw in those inputs? And then for every output, it should also tie logically, semantically, contextually to the previous outputted tokens. And you may even want to pay selective attention to certain words. That's also what we do when we learn. So we read like a para and like we will catch the key phrases or like the important things, and then this happens so subconsciously. And then you would also want to retain the memory or encodings of tokens that are far from each other in the sequence, which we've been discussing in terms of long term memory and those long paths. And if we can parallelize some of these above steps, then nothing like it. Then we can scale. So, with this context now, um, this is so this is our summary so far, short reference window. Then LSTMs just got a little better, and then with this attention mechanism that was introduced in transformers, we can have like really long infinite reference windows. And so this is the paper where really things got transformed using transformers. So this is Attention is All You Need. It was introduced by the Google team in 2017. And to give due credit, attention mechanism was available, it was invented in 2014, but it was still being used with those RNNs. And so this is the paper where we started using attention with this encoder decoder block, and it really revolutionized things. And so now we will start actually building on this. So everything that we learned so far, all the problems, how do these various components address it? So let's cover that. So we want input words as numbers. Okay, so we have input embeddings here, and then you want to maintain the order. So that is your positional encodings. And with both of these, you then have your word, each word with its position encoded and its features encoded. That is what embeddings are. They represent, in a way, the features um, of each word. So an embedding is a vector like that represents your word, And a word could have simply been mapped to a number, right, to feed into machines. But when you have a single number, it's kind of static. It's like a lookup. Whereas if you have like a bunch of numbers that have been used that have been learned and then used to represent that word, then um, say you have so many words in your vocabulary and you use a um, thousand dimension vector to represent each word, and then when you plot them in a thousand dimension vector space. So like we were looking at that z and w earlier, z and y earlier, those two axes, two dimensional, because on my screen I can only show 2D. But if we have thousand such dimensions and you plot these words, and so in that vector space you start seeing different patterns, which words are very similar to each other, and they start forming clusters, and then there are hierarchical patterns. And so that's why embeddings are very important. And then positional encodings, then we want to pay attention to different words in the input itself. And as we saw, we could stack, like LSTM units, we could stack these attention units. So let's call it multi-headed attention. And then all of this is fed forward. So this is feed forward, which is very typical for a neural network, because you have an input and then you maybe have 10 layers, but your output and then the known value while training is only available at the end of those 10 layers. So your input, you want to feed it forward in order for the learning to take place, and then the errors will be back propagated because you would want to apply correction to each layers. But this essentially is about that feed forward. And with this you have your learned vector representation. And so this whole thing together is your encoder module. Okay, and so let's call this coder. And so similarly, you have your decoder module now. So in your decoder module, you will have output embeddings and positional encodings for each output. So initially, when we start off with the decoder module, the first output word would be, say, start of sequence. So that start of sequence default word, SOS, would be used along with what comes in from the input to generate your first output. And that we will feed it back to generate the next word, and so on until you finally generate an end of sequence token. And here you again have your multi-headed attention so that output can learn from previous outputs. And here is a change. You will have cross-headed attention here, because as we discussed, inputs should also be used to learn the output. And then here you will have your feed forward, and now we're almost nearing the end. So you will have a linear layer. And what is this linear layer now? So this is a dense network, dense layer. And towards the end, if you have, say, 10 classes that could be output, like if I were to output the um, animal type given an image, and if there could be 10 animals, that could be my possible outputs. So one neuron for each of those 10 categories, and the previous layer should just feed into each one of those neurons so that it sees everything, and so it's a dense layer. So that is linear. And each of those final output neurons will give you a probability, a likelihood of that neuron, and the highest probability is what is your final output. And so here you would again need a activation function, which we were talking about earlier. And so that activation function in this case in multi-class classification is softmax. And what it does is it gives you an output for each of those neurons, final neurons, but in such a way that their sum across all of them is 1. So it's just like smoothing, and it tries to amplify the most probable outputs, and the ones that are least probable, it tries to diminish them. But this is about our encoder and decoder. And so let's just quickly finish this up here. And then this, as we see, addresses a lot of the issues that we were discussing so far. And one thing that we will cover in detail in our next class, in our next session, is the attention module itself. Like, really, how these vectors, how these attention scores are
Mhm.
generated. And that is going to be very interesting to visualize and to walk through using an example. So that is what we will be covering next time.
Yeah, this is what I was just going to ask. Like one of the questions is, yeah, kind of going a little bit more in detail with every one of those components, and as you said, that will be kind of the objective of the next session, right? To look into those encoder decoder components more in detail.
Yeah, yeah. So like if we do it right now in like one session, it will get
Much.
very heavy,
Yeah.
very heavy. And so that's why we will we have summarized what this transformer
Mhm.
architecture looks like, and then we will continue in our next class, in our next session. But we will just finish this up a bit. So this is your output from each iteration, and this should just feed into your. And with this we are done with our transformer architecture, and this is how it looks like. So this covers everything that we just spoke about: embeddings, positional encoding, multi-headed
Mhm.
attention, feed forward layers, learned vector representation, and this will be explained in much more detail with vectors, examples, deep diving into the math
Mhm.
further later. But this is how it looks like on a high level, and this is the decoder block. And you have again embeddings, output embeddings, positional encodings, multi headed attention, cross headed attention, feed forward, linear layer, softmax, an output that should get fed back in until recurrently until an end of sentence token is generated. And the beautiful part about this is that, say this was your sentence. This is a beautiful cat. And so now that attention mechanism, like how do you learn from that previous word or from a very far away word, is it can be paralyzed because this can just learn from each of these other words. But similarly, at the same time, you can also, because these are matrices, you can also use is to like learn from every other word out there. And so this is how this gets parallelized. It's like a fully connected graph neural network
Mhm.
now. And so this really helps in scaling because we know how massive these LLMs are today. And this is the secret sauce.
Yeah.
And to summarize, just these are the references. So if we want to deep dive into this further, the illustrations here, the slides, all those colorful slides were from StatQuest, and it's a beautiful channel and playlist. So you could go through it.
Awesome.
And that's it for today.
Awesome. Thank you so much, Navina. That's yeah, great presentation. A lot of information, I think for beginners especially, but I really appreciate you breaking it down into manageable pieces so it's easier to digest. There are a couple of questions, especially about the last part. So this transformer architecture, right? This diagram that you drew on draw.io, and then the last slide, I think, before references. So would I guess the first question was, what is it kind of? I'm trying like to kind of summarize it. There is training process, right? There is inference process. So what is this architecture related to? Is it to both of them, or it's yeah? What is it for specifically? So like when do you use this architecture? Whenever training a model, or whenever actually generating outputs from a trained model?
Yeah, awesome question. So, this architecture during training will be used to learn the different
Mm-hmm,
weights that we see on those connections, W1, W2, and so on. So, during training, it will be used to learn those
mm-hmm,
weights. And then during inferencing, it will be used to use those weights to like compute each number that needs to be fed into the activation functions and so on using the now inputs that we see coming in. So your weights are frozen during your inferencing
mm-hmm,
and learned during your training. And then encoder, there are models that are encoder only, decoder only, and then encoder decoder.
mm-hmm,
So our Gen AI models are just decoder only. They are also referred to as autoregressive models because it's like each word is fed back into the next one, and so it's like learning from its previous input, and so it's referred to as
mm-hmm,
autoregressive. So there it's only a decoder only model, so you feed in that embeddings of different words, and it just has during its training learned to like only take that as
mm-hmm,
input and learn the weights here. So that is how these decoder only models work. But because they go through so much massive training, even with only the decoder block they do very well.
mm-hmm.
Yes, and then running both of these during inferencing would have impacted latency, etc. So it's actually only decoder only model.
Yeah, makes sense. Makes sense. And then the second question there was is, could you maybe go over like over this with like some? I know that we'll dive into this like more in detail next session, but high level, kind of what is the um, input and output from expected input and output from encoder and decoder. So like for example, if you take a sentence, right, as you said, like here, an alien or whatever, as aliens entered our planet, so what kind
Yeah,
of, yeah, if we could maybe just quickly go over this again, kind of more as to what encoder and decoder are supposed to do. uh yeah.
for sure. For sure, yes. So as aliens entered our planet, this will be our input. And GPT-2 and those earlier models, they were used for completions. And so with this input, this is what was
Mhm,
generated. And so this will be generated word by word. So like with this input, as aliens entered our planet, um, the first word outputted will be
mhm,
and then the next word outputted will be began.
mhm,
And began will like kind of pay more attention to entered, entered, began. And then the next word to colonize, earth. And then again earth is a planet, so it understands, okay, planet. And so what the next most likely generation, or like what would be a good next word to generate. And so earth, and then it also knows colonize, earth, together, certain groups of extraterrestrials, so it comes up with this word because it saw aliens in the input, and so on. It is able to maintain a very logical trail, like a trail that when we look at, it makes so much sense and it looks creative.
mhm. So this example specifically, it's about this generation stage, right? It's not about this training stage at all, where it calculates like all the weights and come up with them, right? It's specifically like how this generation process would work with an already trained model, right?
Yes, and then during inferencing, it's pretty similar. Like if we were looking at training, if we were looking at training
Mm-hmm,
instead, It's very similar. As aliens entered our planet, the embeddings would be fed in, and then start of sequence post that this would be the first word because it's like a conjunction, and then it starts understanding the grammatical structures, syntactical structures, and so like your first word began and then began and so on, and if there are any mistakes, then it penalizes, then the learning takes place
Mhm.
accordingly. And if during training, it also knows when exactly to stop. So like there's a technique called as teacher training, but it will stop at exactly what it knows with the already known output during training.
Mhm.
So like during training, this entire thing will be fed
Yeah.
in, and this will be the known output, and then it has to learn to generate this known output, and so it will begin word by word, and whenever it makes mistakes, it will be penalized. And because we know the output, it also knows when to stop during training instead of just going on.
Yeah. Uh, well, I'm excited for the next session to dive deeper into this. So, thank you so much again for this high level overview. And yeah, to everyone who's watching, thank you so much for joining us. And yeah, the next event is planned for the next week. So, there we'll actually, as Navita mentioned, we'll dive deeper into the transformer architecture. This was kind of more of why you need to know this, right? And how it works high level. But yeah, please, as I mentioned at the beginning of the session, please go to our website, algofriend.io. We have all our community pages there. Feel free to sign up so you get notified whenever we post the next event. And yeah, thank you so much, everyone. Have a great weekend. Bye bye.